that everyone working in the field of unconventional superconductivity are wearing bluish colors today. So I'm going to talk about unconventional superconductivity in complex superconductors, which are superconductors with multiple degrees of freedom. I would like to thank the scientific organizer for inviting me, and especially also the local organizers, without which I wouldn't be able to stay. These are my collaborators in the past decade, and the contributions of all of them are reflected in this talk. Now I am at Universidade Federal do Rio Grande do Sul. Take your car and go 4,000 kilometers south, and then you will find us. There are both theorists and experimentalists. I would also like to advertise the poster of my master's student, Murilo. We are really looking forward to discussing with you. This is the overview of my talk. The common theme is unconventional superconductivity with multiple degrees of freedom. I will concentrate on the effect of multi-orbital physics. So the additional degree of freedom are orbitals, and another case where the additional degree of freedom comes from either multi-layered system or a sublattice structure. So this is a sample of the many degrees of freedom all of us work with in condensed matter physics. So for the purposes of this talk, let me define what I mean by a simple system and a complex system. I will refer to a simple system to those systems where we can explain all the physics, taking only into account spin and the momentum degrees of freedom. So in the context of superconductivity, this is a BCS theory. So the simple superconductivity has some well-known characteristics, such as the coupling ratio, a specific heat jump, suppression of the spin susceptibility at low temperatures, robustness to impurities, and if there is inversion symmetry, then you don't have coexistence between singlet and triplet superconductivity. Also in simple systems, if the order parameter has the same symmetries as the lattice, then usually we refer to this material as a conventional superconductor. If the superconducting order parameter has symmetries that are reduced with respect to the lattice, then we usually call this as an unconventional superconductors, and then we talk of P wave, D wave, F wave order parameter. But bear in mind that these are really just proxy names for a representation of the crystal group, because you know a crystal does not have full rotational symmetry. In complex systems with more degrees of freedom, however, there are examples, and here I will mention two, for instance, iron-based superconductors and monolayer transition metal dichalcogenides, where the order parameter has the same symmetries as the lattice. Nonetheless, we usually do not think of these materials as being conventional. So there is now a debate of what is an unconventional superconductor. Is it related to pairing mechanism or symmetry? If it's reduced symmetry, I think there is no question that we can call it unconventional. So one example in this talk will be monolayer TMDs, which have these degrees of freedom. And another example that I will mention are multi-layered or multi-sublattice systems, such as cerium, rhodium 2, arsenic 2, and also bilayer TMDs. They display the very same physics under a magnetic field. So let me mention some phenomena that we observe in complex superconductors. I will concentrate on impurities and the response to magnetic field. In simple superconductors, the response to impurities allowed us to distinguish between conventional and unconventional superconductivity. I will also explain that this is not the case anymore in complex superconductors. One example is strontium ruthenate, which is of course a complex material, and the order parameter is debated. But here I show a well-known plot. On the vertical axis is Tc, on the horizontal axis is residual resistivity, and residual resistivity is usually proportional to the amount of impurities in the material. So you see that the impurities quickly obliterate the superconducting state in strontium ruthenate. So because of this, it's very, very likely that the superconducting state here is unconventional. A different example is magnesium diboride. Here again, we have Tc and resistivity, and each point in this scatter plot is a different sample with different qualities. And notice that Tc does not vary appreciably. And if you apply a simple theory of two-band superconductivity, this would predict that superconductivity should be suppressed in a two-band superconductors. But this does not happen in magnesium diboride. And I will shortly explain that this is related to the additional degree of freedom in this system. Complex systems also have unusual response to magnetic field, which I will address for these two systems. I will just quickly mention other behaviors found in complex materials, which I will not talk about. Just a sample of them are collective modes, such as Leggett modes, anomalous Hall effect, Bogoliubov Fermi surfaces, odd frequency pairing correlations. If some of you are interested in this stuff, I would happily discuss them. Let's get into monolayer TMDs. So here we have beyond spin and momentum degrees of freedom, we also have an orbital degree of freedom. Monolayer TMDs, they are part of the family of 2D materials. They are usually regarded as the more complicated siblings of graphene. You can find them in their metallic forms and also in semiconducting forms. The semiconductors, you can either dope or gate them, such they also become superconducting. Monolayer TMDs, they are also Ising superconductors. Ising superconductors are the simplest family of non-centrosymmetric superconductors there are. Perhaps the most famous non-centrosymmetric superconductors is the Rashba superconductor. You take a 2D superconductor, put it on a substrate, which induces Rashba spin-orbit coupling. But Rashba has two components. Ising superconductors only have one Z component, and this is why they are the simplest superconducting, lacking the inversion center. You can get an easy superconductor by putting, for example, a lead monolayer on a silicon substrate, or intrinsically in monolayer TMDs. And here I will talk about the hexagonal TMDs. And everything I'm about to show applies to all of them, but I will use niobium diselenide as the working example. The origin of Ising spin-orbit coupling is fairly straightforward to understand. Here I show the crystal structure of niobium diselenide. The vertical lines, they divide the unit cells, so you see that each unit cell has a niobium atom and two selenium atoms. Most of the electronic weight comes from the niobium d orbitals, but the d orbital electrons, they feel a crystal electric field coming from the selenium atoms, and this electric field points strictly in the in-plane direction. And if you remember electrodynamics, if transport is in the plane, then V cross electric field gives you a spin-orbit magnetic field, which points strictly along the z-axis. So depending where you are in the unit cell, the spin-orbit field points either up or down, but never in the in-plane direction. So you can imagine that when you apply an in-plane magnetic field, and then you have a Zeeman effect, this magnetic field will have a very hard time destroying superconductivity because the spin-orbit coupling locks the spins in the z direction. So this is observed in many materials. This is one example, one well-known example in niobium diselenide. On the vertical axis is magnetic field, horizontal axis temperature. The dashed line shows the Pauli limit, and the blue line is the monolayer. So you see that the critical field exceeds the Pauli limit by quite a lot. And at low temperatures, we cannot even reach, I mean experimentalists, we cannot even reach the Pauli limit. But all of this is related to spin physics. Now, let me go to the complex model, which is necessary to capture how the system responds to impurities. So we cooked up a tight binding model considering all the niobium atoms. Each niobium atom has 3 d orbitals. For simplicity, I will refer to the orbitals as the red one, the green one, and the blue one. The first term are the hoppings. The second term is Ising spin-orbit coupling, which stems from the in-plane green and blue orbitals. Then we add a Zeeman magnetic field. There is no coupling to spin because there is no orbital effect because the magnetic field is applied in plane. And we are doing this in real space, so we can also add impurities, on-site impurities, which are usually the strongest type of impurities to destroy superconductivity. By the way, if you're interested in the numerical techniques involved in this, it's quite fun to discuss this as well. In the special clean case, we can Fourier transform everything to momentum space and then obtain the bands, the electronic structure. Since there are 3 orbitals, there will be 3 bands, but because of spin-orbit coupling, these are split into 6. If you want to study superconductivity, all that matters are the bands crossing the Fermi level. So on the right, I show a 3D version of the band structure. The gray hexagon is at the Fermi level. So the intersection between the 3D bands and the hexagon allows us to visualize the Fermi surface. So you see that, So the Fermi surface is composed by a center red pocket completely dominated by the z² orbital. And at the k and k prime corners, the orbital content is completely dominated by the green and blue orbitals. Now we would like to study superconductivity. And to do this, we assumed the simplest type of pairing we could. So we started with a pairing interaction in the singlet channel, so a singlet on-site intra-orbital pairing only. There's a good reason for that by looking at the electronic structure, because if you look at the colors, at the orbital content, and analyze the orbital content available at opposite momenta, you see that if you have a red at 1k, you also will have red at opposite k. So interorbital pairing is rather unlikely in this system. After solving this, we also can look at all the pairing correlations. And these will be very exotic. In there, we can have singlet, triplet, on-site, intersite, interorbital, everything. Of course, we do reproduce the enhancement of the critical field. So in the middle figure, the dotted line shows the case without spin-orbit coupling, and the solid line shows the case with spin-orbit coupling. So we see the enhancement. We also can see what happens inside the phase diagram, which each one of the magnetic field, but this is well-known spin physics. Here I'm looking inside the phase diagram and looking at the pairing correlations. And this is a zoo of different pairing correlations. If someone is interested in discussing these type of things, we can do this after the talk. So if we apply the simple theory, a simple superconducting theory to monolayer TMDs with spin and momentum degrees of freedom, then this theory predicts that on-site impurities, they actually suppress the critical field. The reason for that is that on-site impurities, they counteract the easing spin-orbit coupling, in this way destroying superconductivity. So the first thing we tried to do in our complex model was to reproduce this paper here, which is a very nice paper. We checked all the calculations of this paper. It's very well done, and we think it's correct. So we used this as a test, but we did not see a suppression of the critical field numerically. No suppression whatsoever. So this was very, very puzzling at the beginning, but we later understood where does the robustness come from. So here is the explanation. So here is a simplified picture of the band structure. And although this is a complicated 3-orbital model, we can diagonalize the Hamiltonian exactly at high symmetry points. So solving the Hamiltonian at 3 points, gamma, k, and k prime, we obtain that the orbital content at k is d plus id, at k prime it's d minus id, and at gamma it's dz squared. Now, all of these 3 orbitals, they are orthogonal, which meaning that if we take the internal product, this gives 0. So for the remaining of the argument, I will exclude gamma, but this is really just for simplicity. We can easily reintroduce it at the end. So at these high symmetry points, at k, gamma, and k prime, C3 rotation is a symmetry at these points. In the vicinity of these points, the C3 symmetry remains approximate. So here goes the argument. I hope I didn't lose the attention. Let me go through it. It's really simple. So we consider a C3 symmetric scattering potential, V. Then, so if it's C3 symmetric, then V commutes with C3 rotation. In the first line, we see how the C3 rotation acts on each of the orbitals. So you see that C3 accumulates a minus I 2 pi over 3 phase for k. It's in the other direction for k prime. So if the commutator is 0, then we can form this expectation value, which of course also must be 0. Then we act with the C3 rotation operator on the states using the properties above. And then we immediately come to the conclusion that this scattering element K prime Vk is equals to 0. Putting this mathematics into words, there is no scattering between K prime and K. So summarizing everything, there is no scattering between K prime and K, and the physical reason is that the orbitals are orthogonal. There is no scattering between K prime and gamma because the orbitals are orthogonal. There is also no scattering between gamma and K because, again, the orbitals are orthogonal. Also, there is no scattering between one band at K to the other band of K because non-magnetic impurities do not flip spin. So you have a very special band structure where the orbital content protects it against on-site impurities. And I think that a partial interesting message here is that this even works, and I tested it for if I started with triplet superconductivity, which in a simple model would be completely obliterated by the impurities, but here would remain completely robust. So maybe by exploring triplet superconductivity in multi-orbital systems, where you have this type of orbital protection, is a way of getting the triplets to survive the impurities. Let me go now to another system, which is a class of bilayer systems. Here I will not have additional orbitals. Here the additional degree of freedom will be either additional layers or an additional sublattice structure in the unit cell. One example is cerium, rhodium 2, arsenic 2. On the right I show the crystal structure. Here CE1 shows the first sublattice in the unit cell, and CE2 is the second sublattice. Because of the crystal environment, each sublattice experiences a Rashba spin-orbit coupling, which has a helical in-plane texture. So both sublattices have this texture, but in opposite direction. So this leads to an intriguing phase diagram, which I will explain shortly. The exactly same situation, not the same situation, a similar situation happens in bilayer niobium diselenide. So here, instead of a sublattice, I have different layers. And instead of Rashba spin-orbit coupling, I have Ising spin-orbit coupling. So the same phenomena that is observed in the cerium compound for a perpendicular magnetic field, I should observe for bilayer niobium diselenide for an in-plane magnetic field. So the minimal model that I'm about to show treats both systems and perhaps other systems at the same time. So this is now a very simple toy model, and up to now everything was numerical. From now on, everything will be is obtained analytically. This is a BDG Hamiltonian. The first term has the intra-layer hoppings. The second term's inter-layer hoppings. I could use either Ising or Rashba spin-orbit coupling. I will talk about Rashba spin-orbit coupling, but everything is applicable to the Ising case as well. So here I have Rashba, and the last term is a perpendicular magnetic field. And here I am looking at the case where the magnetic field is perpendicular to the spin-orbit texture. Since we didn't want to limit ourselves to a specific material, we did a brute force study, and looked at all 16 possible order parameters that this system could have. I'm of course not going to talk about all of them, but if you want to know about all the exotic triplet possibilities, I'm happy to discuss them as well. So here I list on the right are all the 16 possibilities. I will only look at the singlet options, at the intralayer singlet order parameters. If we didn't have an additional layer, then the only possible singlet would be which I call an eta 00, which is an even singlet order parameter, where the order parameter has a plus sign on one layer and also a plus sign on the other layer. But since I have an additional degree of freedom, I also can have the same type of singlet, but where the order parameter has a plus sign on one layer and a minus sign on the second layer. Which one dominates is now, of course, an issue of analyzing the instability condition. We can also look at this from the point of view of the wave function. With only one layer, I have the first line. The second line shows what happens with the possibilities with the additional degrees of freedom. So the yellow would be the even singlet, and the blue is an odd parity singlet. So in simple systems, only triplets could be odd parity. But since this is a complex system, now I also have a singlet odd parity possibility. Let us discuss the properties of the even phase. For this, I begin with a 2D superconductor, apply a magnetic field along the z direction. Here I assume that there is no orbital effect, and I also assume that the transitions are of the continuous type. If I now add a substrate, and here I'm adding a substrate just for didactic reasons, but in cerium, rhodium 2, arsenic 2, this happens intrinsically because of the crystal fields. So because of Rashba spin-orbit coupling, now the magnetic field has a harder time destroying superconductivity. So you see the larger alpha, which is spin-orbit coupling, the greater the critical field. Now add another layer, but invert it, so that globally there is inversion symmetry, but locally on each layer you break inversion symmetry. Of course, since they do not couple, the phase diagram is identical. Now we couple both layers, and now interlayer hopping now couples two layers with opposite Rashba textures, so they cancel each other out. And this is why interlayer hopping suppresses the critical field. So there are now two important energy scales at play. One is spin-orbit coupling, which is alpha, and the other one are the interlayer hoppings, which is T. As long as alpha over T is larger than 1, we can speak of reminiscent effects of a non-center symmetric superconductor, but in a globally inversion symmetric system. Now, let us repeat the same exercise, but for the odd phase. In the odd phase, the only difference is that one layer has a plus order parameter and the other layer has a minus order parameter. Up to now, everything is identical as the even phase. Now we communicate the layers. Here, the dashed lines is still the even phase for comparison purposes, and the new odd phase is shown by the solid green curve. So you see that the solid green curve has a TC that is suppressed. However, whereas the even phase suffers due to the magnetic field. The odd phase is robust against the magnetic field. So now to obtain the true critical field, you should look at the combined dashed green and solid lines. And this typically gives us something like this, where you should look at the solid black line, where at high magnetic fields there is an odd phase, and at low magnetic fields there is an even phase. And since you cannot continuously deform one order per meter into the other, the transition necessarily needs to be of the discontinuous first order type. Now we look what happens if we add impurities. So this is done within the self-consistent Born approximation. I now added a third parameter that is changing, which is gamma. This is the scattering rate. Here I use somewhat more realistic parameters. Alpha and T, they go from 0 to 60, and gamma only varies from 0 to 10. Usually, for an unconventional superconducting, an odd parity state, these states are usually obliterated for a scattering rate of the order of 1. So here again, the red solid line is the disordered odd phase, and the red dashed line is the even phase. The even phase, you see that disorder even enhances the critical field, which is very peculiar effect. The physical reason for that is that the scattering rate counteracts the effect of interlayer hoppings, thus restoring a little bit of the effect of the easing protection. But the odd phase is clearly sensitive to the impurities. However, it's much more robust to impurities than a simple unconventional state. So we can map out a phase diagram to see where in parameter space this odd phase is robust. The color code shows the critical scattering rate necessary to obliterate the odd phase. The even phase cannot be obliterated. The vertical axis is spin-orbit coupling, the horizontal axis is interlayer hopping, and you see that there is an appreciable region which is quite robust against impurities. So my time is up. I leave you with my conclusions, and thank you very much for the attention.